In this video, we're going to talk about rotational kinematics. Now that all the definitions for rotational quantities have been covered, we're ready to discuss the motion of rotating rigid bodies. In other words, rotational kinematics. First, let's review the equations for our translational kinematics. This was one of the first topics that we covered. These equations are only valid for cases involving a constant acceleration. Okay, so if the acceleration changes, these equations are not valid. Okay, this allows gravitational problems to be solved where A equals G, and it makes it possible to solve kinematic equations without advanced calculus. When acceleration changes, the problems become a lot more complex, so we're going to assume the acceleration remains constant, just like we did for the kinematic equations. Okay, here are the equations that we had for our kinematics index card. And again, remember that we use vectors because they have magnitude and direction. And again, remember that I'm not going to do this for the rotational equations. Okay, there's another one that's missing here, but it's really this here, this equation here, and we substitute it into the equation for our definition for velocity. Velocity is the displacement per unit time. So remember, we define this as being delta x over delta t. Okay, and if you substitute this here into this equation right here, you get that final fourth equation that I gave you, which is delta x equals 1/2 times v final plus v initial all times delta t. Okay, so for each of the translational kinematic equations, there's also an equivalent rotational equation. So all you do is you replace your v with omega. You replace the theta with delta x, and you replace the a's with alphas. So here we go. If this is your kinematic equation, remember that we've defined v as being r omega, and a is defined as r alpha. So if you substitute in v and v naught and a with r omega naught, and r alpha, you'll see that all three terms have an r in it, and you can cancel that out. And what are you left with? Omega equals omega naught plus alpha t, which is the same format as your kinematic equation. So here are your kinematic translational equations. These are the equivalent rotational equations. Okay, so what I would recommend you do is make sure that you can find these equations on your index card, or put them on your index card, just like you did for your kinematic equations. And then I recommend that you take these equations and make sure you can find them on your formula sheet, because you're not going to be given your kinematics card for your rotational test on the AP Physics test. You're going to have to use their formula sheet. Okay, so the rotational motion equations also work as part of the equations for rolling motion. Rolling motion is simply rotational motion and linear motion combined. So think of it as a wheel on a car. It's rotating, it's showing rotational motion, but it's also moving forward as it rotates, and this shows linear motion. Thus, we can use the translational and rotational kinematic equations to solve rolling motion problems. A bicycle wheel with a radius of 0.30 meters starts from rest and accelerates at a rate of 4.5 radians per second squared for 11 seconds. What is its final angular velocity? Go ahead and pause the video and look at the equations we just went over and solve for the see if you can solve the answer. Okay, so let's take a look and see if you got it. The correct answer is D, 50 radians. We are given a radius, we are given alpha, and we are given t. We also know that omega naught is 0. Okay, We want the final angular velocity. The only thing we're not given is the displacement. So since the angular displacement isn't given, you're going to use V final minus V initial equals, omega final minus omega initial equals alpha t. A bicycle wheel with a radius of 0.30 meters starts from rest and accelerates at a rate of 4.5 radians per second squared for 11 seconds. What is the final linear velocity? Okay, go ahead and pause and see if you can get this one. Okay, so let's see what the correct answer is. It should be B, 15 meters per second. They're giving you angular quantities. Okay, they give you the radius. You start from rest, which is omega naught. You have alpha, and you have t. You're going to solve for omega final. And then you're going to have to convert omega final to V. Okay, and that will give you 15 meters per second. A bicycle wheel with a radius of 0.300 meters starts from rest and accelerates at a rate of 4.50 radians per second squared for 11.0 seconds. What is its angular displacement during this time? Okay, go ahead and pause the video and see if you can solve this one. Okay, the correct answer is B, 273 radians. Okay, so let's look at this. We're given R. We have omega naught. It is 0. We have the acceleration alpha, which is 4.50 radians per second squared. We have t. It's 11.0 seconds. We want the angular displacement. The only thing we don't have here is we don't have the final angular velocity. And so that means we're going to be using the angular displacement is equal to omega naught t plus 1/2 alpha t squared. Substitute in your numbers, you should have gotten 273 radians. A bicycle wheel with a radius of 0.30 meters starts from rest and accelerates at a rate of 4.5 radians per second squared for 11 seconds. How many revolutions did it make during that time? Go ahead and pause and see if you can solve this one. Okay, so let's see if you have the right answer. You should have gotten C, 43 revolutions. Okay, so let's go ahead and look at the next one. A bicycle wheel with a radius of 0.30 meters starts from rest and accelerates at a rate of 4.5 radians per second squared for 11 seconds. What is its linear displacement during this time? Go ahead and pause the video. Okay, so let's see if you have the right answer. You should have gotten B, 82 meters. Okay, I'm not going to go over any more of these. Hopefully you're getting the hang of it. If you need to go over these, go ahead and do them, and then just let me know in Edmodo that you need the answers. And then I'll go ahead and supply them for you in, the next day in class. Okay, in the next video session, we're going to do rotational dynamics.